Hi everyone. So today I'm going to be presenting hybrid fuzzing on the Linux kernel from a paper from NDSS in 2020. So hybrid fuzzing will also stands for HFL, which I will be referring to throughout this entire presentation. So this paper is about automatically finding vulnerabilities in the Linux kernel, which is one of the most um, critical components to any operating system. So, in this paper, the authors really propose a system called HFL, which combines traditional fuzzing and concolic execution, but in a way that actually works for the kernel level software. So, the key idea of is fuzzing and concolic execution each have strengths and weaknesses. And if we can combine both of these methods carefully um, and engineer around some of the kernel specific problems that arise, we can do a better job in finding vulnerabilities in high privilege software than either of these methods alone. So, some of the key terms I want to go over in this presentation are first is traditional fuzzing. So traditional fuzzing is a process that automatically generates large numbers or of random or slightly modified inputs, and it runs them in a program to see if it crashes or behaves incorrectly. So it's really fast and it's scalable because it doesn't really try to understand the program's internal logic, but it really struggles when programs have complex conditions and constraints, they require specific input formats or multi-step validations or something like that, because random mutations usually don't satisfy those complex conditions. And we're going to get a little bit more into some of the limitations with traditional fuzzing later in the presentation as well. So the next thing I want to discuss is concolic execution. So concolic or symbolic execution, I'm going to be using both interchangeably. So it's a process that happens when a program is executed with real inputs, while also tracking the symbolic constraints with each execution path. So these constraints are really sent to something called a solver to generate new inputs that force a program down a specific unexplored branch. So this makes it much better at handling some of those complex conditions that traditional fuzzing, it doesn't really handle. So the trade-off is that constraint solving is computationally expensive. So this is method is computationally expensive, so it can slow down and be very resource intensive. So this is what will lead to hybrid fuzzing. Hybrid fuzzing combines both of these methods of traditional and concolic execution, and it combines them and it takes the speed of traditional fuzzing and it takes the precision of symbolic, or concolic execution. So the fuzzer explores um, broadly and efficiently. So when it encounters a branch it can't really get past, that's where symbolic execution is kicked in and it's used to help generate some of those inputs that could satisfy some of those difficult constraints or conditions. So this balance really improves both the coverage and efficiency. And later in the presentation, we're going to discuss how this is going to could arise and be used when testing and finding vulnerabilities in the Linux kernel. And then finally, we have the kernel. So the kernel is high privilege software, and specifically in this context, fuzzing an operating system's kernels is significantly more complex than just fuzzing any program that typically runs in the user space. So kernel fuzzing really has to deal with things called indirect control transfers, system call sequences, and even like different stateful interactions. And these are complex situations and they can really contain deeply nested data structures, passed as arguments. So this characteristic, of the kernel makes input generation and path execution more challenging. So that's the problem that this paper really focuses to tackle. So, just to recap some of the things that we went over, this slide really highlights some of the core trade-offs that we're going to get into a little bit more deeply, as throughout the presentation. But traditional fuzzing is fast, but it's really limited because it can't cover some of those complex conditions. And then concolic execution is powerful. It can cover those complex conditions, but it's also expensive and it's pretty resource intensive. And hybrid fuzzing really attempts to combine both of these strengths. So especially in challenging environments like the Linux kernel. Okay, so now to get into why fuzzing matters and what this process of fuzzing really looks like. So if you look at this diagram on the bottom, this kind of shows how the general process of fuzzing really looks like. So starting from the left side, you can see some of the initial inputs. So these are basically your seed inputs. They might be, if we're talking about the kernel, let's assume like they're very simple, a valid system calls that, are going to work. They're simple. So those inputs can go into this fuzzer loop that in the center that I'm going to talk about. So inside this loop, there's really three main things that happen. So the inputs get mutated, and then after they get mutated, those interesting inputs that are relevant to us, those get selected, and then we monitor the program. So when the input runs, the fuzzer tracks the coverage, meaning which parts of the program are executed. If the input reaches new code that hasn't been there before, it gets saved into something called a corpus, which is kind of like it's like a collection of useful test cases that can be added to, and you can add to that. So those inputs get mutated again. So like really, if we're looking at this visually, the arrows in the diagram show this constant feedback loop. So you run, you monitor, you mutate, and then you really repeat this process. So, and this is why fuzzing actually scales really well. It just keeps trying different things, and it keeps whatever is working. But now, if we imagine, uh, software or code that has a lot of deep branches. Like for example, in the kernel, imagine like a deep branch in the kernel that requires a really specific value to get triggered. Random mutation might not even hit that exact value, might not cover it because it's very specific. So this is kind of some of the limitations that also arise with your traditional fuzzing logic. Okay, so now if we're talking about, concolic execution, if we look at this diagram, on the left, there's like a small code snippet in the middle. So I want to talk about this. So there's so so you can see that this is called the program control flow graph, and inside you can see, so this is a better picture of it. So inside you can see each block kind of has a basic block of code, and on the right you can also see the branching tree. So these are the kind of two examples I'm going to be going over. So each time the program encounters a conditional, like either an if statement, the symbolic execution path actually splits into two. So in the tree, each fork kind of represents a branch condition. So instead of guessing what values, randomly, symbolic execution records these conditions, like if x must be greater than 10 or y must equal some number, some value. So it asks the solver to compute those specific values that are going to satisfy those conditions. So visually, you can see how, this execution tree really grows downward, more if statements and more branches that are encountered. So it's actually very good at being precise and really targeting those specific values. So we're going to talk about some of the weaknesses you see um, in the next slide. So just, this is how it gets evaluated. Okay, so now we can talk about some of the trade-offs of, concolic execution. Okay, so before I, cover these bullet points, let's take a look at this diagram. So if you look at this tree diagram, you can really see that every conditional branch really splits into two possible paths. So after one branch, you can see that there's two paths. And then after two branches, there's four. After three branches, there's eight. And it really just keeps doubling. So this is called state explosion. So in small programs, this is pretty manageable. But when you get into more complex programs like the Linux kernel, which contains thousands of branches, loops, and state transitions, the number of possible execution paths grows exponentially and really like very immediately. So each path must really store its own constraint, and each path requires, a different solver query, and each solver query becomes more complex as more of the conditions accumulate. So the problem isn't that there's just a lot of paths, it's that each path also becomes pretty computationally expensive if you want to analyze it. And this leads to the second drawback, which is the solver cost, and it really limits your scalability. So every time concolic execution tries to flip a branch, which basically just means it tries to collect constraints to an SMT solver. Uh, if those constraints involve pointer arithmetic, nested structures, or kernel state, solving can take really seconds or even longer. And when it comes to fuzzing, the speed actually really matters. So traditional fuzzers can execute thousands of inputs per second. And if symbolic reasoning takes seconds for just one input, the entire process really slows down. And this is where you can see like there really is a clear trade-off. Fuzzing is fast, but not really as precise, but symbolic execution is precise, but it can be slow. And that's why hybrid fuzzing uses concolic execution really selectively. Only when, random mutations get stuck on like those specific tight branch conditions. So, again, so some of the trade offs are high precision for state constraints, exponential path growth, expensive constraint solving, and really poor scalability when it comes to large stateful systems like the kernel. Okay. So now if we take a look at this diagram just one more time, you can see. Okay. So now I really want to get into how hybrid fuzzing works and how both of these methods are really used. And I'm going to really get into this diagram. Um, yeah. Okay. So, on the last slide, you could see on the left side, we have a coverage guided fuzzer. So okay, so it generates inputs and places them into a queue. So that queue feeds those inputs into something called a target program, which in this case, if we're thinking about our kernel, it is our kernel program. So yeah. So on the right, we can see the concolic execution engine. So when the fuzzer hits, a branch that it can't flip, again, meaning that it just always evaluates the same way and it's not changing the way it evaluates. So when the fuzzer hits that specific branch, it then sends that input over to the symbolic engine. So this symbolic engine takes that input and analyzes that specific path that was not being flipped. It collects those constraints and it solves for new inputs that could possibly fix that problem and flip that branch. So then that new input goes back into the fuzzer's queue. So visually, if you're really looking at it, you can see that there's this back and forth loop between the fuzzer and the symbolic engine. So the fuzzer handles the exploration of, pretty broadly, but that symbolic engine is able to handle some of those precise branch conditions and able to, you know, handle those ones. So this loop is really the heart of what hybrid fuzzing is and how it works. Yeah, so okay, now we can go back and okay, so now that I've covered hybrid fuzzing, I've covered concolic execution, we've covered traditional fuzzing. Now let's talk about the kernel a little bit and why this is important, why this is significant. Okay, so you can see yeah, like how this architecture is pretty layered. So on the outer layer, you have your application layer. And now let's really dig into why the kernel is important. So this kernel, you can see in this diagram, the kernel runs in ring 0, which is the most privileged CPU mode. This means that the kernel has unrestricted access to a lot of the memory systems and hardware. It manages, memory allocation, and protection. It schedules processes. It handles device drivers, file systems, system calls. So to put this into context, if a program running in the user space, if that crashes, only the application stops running. But if the kernel crashes, the entire operating system crashes. That is the key. That is why it's important. So if you're thinking about it this way, if there's an attacker and they exploit, a vulnerability in the kernel, like let's say such as a buffer overflow, or maybe it's a use after free issue, they can potentially gain arbitrary code execution at the kernel privilege. So this could mean that your whole system is compromised, and they could possibly escalate their privileges, disable security mechanisms, or install different softwares that could really be detrimental and really crash the whole system. So the kernel also exposes, a large attack surface. So every time there's a system call, such as an open or a read or a write or a memory mmap, it's really an entry point into the kernel code. Many of these calls accept complex nested structured arguments. So not only is so the kernel is really highly privileged and it's pretty exposed. That's why protecting it is so important. And that's why this paper is important, is because if the kernel is compromised, the entire security, of the operating system is also collapsing. So that's why kernel fuzzing is really important, and it's also a challenging, you know issue to tackle. Okay, so I'm going to talk about some of the three main challenges that I'm picking out to talk about. So so while testing the kernel, so the first one is indirect control flow. So in the kernel, if you call a function, instead of, writing just a basic, if, for example, we have a function called a, and, you're not doing it if, this parameter is equal to 1, call a. If you call a function through something called the function table, so visually, instead of branching explicitly to that function, the program has to jump indirectly through that function table. So this actually makes it harder for fuzzing a fuzzer to guess the exactly right index, and the symbolic execution struggles with and symbolic execution also struggles with indirect pointer dereferencing, through this function table. So that is, an issue that comes up. The second are system call sequences. So imagine calling, a read before you call open. It's gonna fail immediately. Now imagine if you have more complex code where system calls really depend on the IDs created of previous system calls. If fuzzing calls them in the wrong order, the execution can just stop. Um, so that is also a problem and that we encounter. And the third one is having nested arguments. So the kernel a lot of the time will copy structures from user space into kernel space. So one structure can contain a pointer to another buffer, and it can also have like a length field that specifies how big that is. So without understanding that memory layout, fuzzing kind of can build invalid inputs that really fail before reaching that deeper condition or deeper logic. So, if we're looking at this, like execution can just stop early because of these issues. So that are some of the issues that come up with kernel testing. Okay, so now we're gonna walk through some of HFL's key ideas. So let's walk through this architecture diagram. So at the top, you can see the static analysis and kernel translation. So before fuzzing begins, HFL rewrites the kernel code. So it converts all of the indirect function pointer calls to direct conditional branches. So instead of jumping indirectly through the function table, it really expands into some of those explicit if statements. So this really helps the symbolic reasoning process, and it makes it much easier. So the next thing is the system call sequence. So HFL uses something called static uh, points to analysis to find some of the candidate or read or write pairs between system calls. So then during some of the symbolic execution, it checks whether those dependencies actually are occurring at runtime. So if they do, HFL learns that one system call has to precede another. So yeah. So this information is fed back to the fuzzer, and finally some of the nested argument retrieval. So that issue is addressed. So when HFL monitors some of the functions from functions like copy from user or whatever. Whenever the kernel copies data from a user space, HFL tracks, the buffer pointer, the size of the argument, and the offset within the structure. So using this information, it's able to reconstruct some of the nested structure layout. So visually, the system integrates static analysis, kernel rewriting, runtime validation, and symbolic execution and fuzzing. And they all work together in a loop. So some of the significance and results of the paper. So briefly, I'll discuss some of the findings in the paper. So HFL discovered that 24 previously unknown vulnerabilities and 17 were confirmed by Linux developers. So it really, what it did was it achieved higher coding coverage compared to some of the previous methods from Syscolor and Moonshine. So code coverage means that the percentage of code that was, executed during uh, testing. So that was higher, and more of the kernel's logic was explored, which was the goal. And more exploration in this context really means that there's more chance of discovering some of those bugs. So, you know, at the end of this, to conclude, what hybrid fuzzing, really means is hybrid fuzzing really shows that it can scale to the Linux kernel, not only when it's adapted to indirect, but so it can scale to the Linux kernel, but it can only scale when you have to address these issues and adapt to handle some of the issues that are present within the Linux kernel, such as indirect control flow. system call dependencies, and nested arguments. So it's not just combining two techniques. It's really creating a technique that involves both concolic execution and traditional fuzzing to address these kernel specific issues, and really engineer a solution that can work around these issues. And at the end of it, that's why this paper is very impactful. And I really encourage everyone to really read the details and in depth of how, this was done and explored. But yes, that is the end. And these are the citations. All right. Thank you.